4 billion miles from where you're sitting right now, something is missing. Not an object, not a moon, not a spacecraft, a color, a single exact wavelength of light that should be there, that has to be there according to every rule we know about physics and chemistry, and it simply isn't. And the strangest part isn't that scientists found this missing light on Pluto. It's that when they went looking somewhere else entirely, on a moon of Saturn 1 billion miles closer to the sun, wrapped in a thick orange atmosphere, drenched in methane rain, they found the exact same gap, the exact same missing color, on two worlds that have almost nothing in common. And right now, in laboratories across the world, some of the most respected planetary scientists alive cannot tell you what is causing it. This is not science fiction. This is not a leaked report or a rumor from an anonymous source. This is a real, peer-reviewed, still unfolding discovery from the James Webb Space Telescope. And by the time you finish watching this, you're going to understand exactly why it has some of the sharpest minds in astronomy quietly unsettled. Let's start with what light actually tells us, because you need this to understand why this discovery matters so much. Every single element, every molecule, every chemical compound in the known universe absorbs light in its own unique way. Think of it like a fingerprint. If you shine white light through a gas or bounce sunlight off the icy surface of a distant world, certain very specific wavelengths get swallowed up. They vanish, not randomly. Each molecule steals its own particular slice of the light spectrum, and only that slice. Astronomers call these dark gaps absorption lines, and they are basically the only way we have of reading the chemical menu of a place we will never physically visit. When you point a telescope at a planet 1 billion miles away and break its light apart into a spectrum, like a rainbow stretched out and analyzed pixel by pixel, those missing slivers of color tell you, with near certainty, what that world is made of. Water leaves a signature. Carbon dioxide leaves a signature. Methane, nitrogen, ammonia, all of them, cataloged, known, matched against enormous databases built up over decades of laboratory work here on Earth. So when the James Webb Space Telescope, the most powerful infrared observatory humanity has ever built, pointed its instruments at Titan, Saturn's largest moon, scientists expected exactly this. They expected to see the fingerprints of nitrogen and methane, the two gases that dominate Titan's thick, hazy atmosphere. And they did see those, but buried inside the data was something else. A dip in the spectrum at a very precise point, 113 micrometers, deep in the infrared range, human eyes could never perceive. And it didn't match anything, not methane, not any of the complex organic molecules known to exist in Titan's smoggy orange atmosphere, not anything sitting in the reference libraries that planetary chemists have spent their careers building. At first, that kind of anomaly gets treated the way any good scientist treats an anomaly, with suspicion, not excitement. Instruments have quirks, detectors have artifacts, data pipelines have bugs. Nobody wants to announce the discovery of a mystery molecule, only to find out 6 months later that it was a smudge on a mirror or a calibration error in a piece of software. So the team did what serious scientists always do. They checked, and checked again. They pulled the signal out of two completely separate instruments on Webb, the near-infrared spectrograph and the mid-infrared instrument, two different detectors built by different teams, calibrated in different ways, looking at light in overlapping but distinct ranges. If this was some kind of instrumental glitch, it should only show up in one of them, or show up differently in each. Instead, the exact same absorption feature appeared in both. Same wavelength, same shape. Confirmed independently, twice on the same object. That's the moment an anomaly stops being noise and starts being real. Here is where the story could have simply ended, filed away as an interesting but contained curiosity about one moon of Saturn, an unidentified molecule in Titan's atmosphere. Strange, worth investigating, worth a paper, but ultimately a single-world mystery. Except one of the scientists working on the Titan data, a researcher named Bizarre, had a thought. Titan is not the only icy, distant, chemically active world Webb has been staring at. Pluto, the dwarf planet sitting in the frozen outskirts of our solar system, over 3 billion miles from the sun, had also been photographed and spectrally analyzed by Webb back in May of 2023. And Pluto's surface chemistry, its nitrogen ice, its methane frost, its tholins, those reddish-brown organic compounds that give Pluto its rusty color, had been cataloged in detail by earlier missions like New Horizons and ongoing Webb observations. So Bizarre reached out to a colleague, Emmanuel Lelouch, who had been working directly with the Pluto spectral data. And he asked him one very simple, very direct question. Do you also have a signature at this exact wavelength? Think about what that question actually implies. Titan and Pluto are, in almost every meaningful sense, opposite worlds. Titan has a dense atmosphere, roughly 50 times the surface pressure of Earth's own air, thick enough that spacecraft have literally parachuted safely through it. It is warmed, relatively speaking, by its position near Saturn. and its surface hosts liquid methane lakes and seas, an alien hydrological cycle running on hydrocarbons instead of water. Pluto, by contrast, sits in a deep freeze at the ragged edge of the solar system, so far from the sun that sunlight itself takes over 5 hours to arrive, so cold that nitrogen, the same gas that makes up most of the air you're breathing right now, freezes solid onto its surface like snow. Pluto's atmosphere is almost impossibly thin, a whisper compared to Titan's crushing blanket of gas. These are not sibling worlds. They are not formed from the same material in the same part of the solar system. If you designed an experiment specifically to test whether two wildly different planetary environments could somehow produce identical chemistry, you would struggle to pick two better test subjects than Titan and Pluto. And yet, when Lelouch checked, the answer came back yes. The same missing wavelength, the same 5.113 micrometer gap, showed up in Pluto's spectrum too. That is the moment this story tips from curious to genuinely strange. Two worlds separated by roughly 1 billion miles of empty space with drastically different temperatures, drastically different atmospheric pressures, drastically different formation histories are apparently sharing a chemical fingerprint that doesn't belong to any molecule currently known to science. Whatever is producing this signal isn't tied to one specific planetary environment. It isn't something unique to Titan's methane seas or Pluto's nitrogen ice. Something about the underlying chemistry, something fundamental enough to survive wildly different conditions of heat, pressure, radiation, and composition, is producing this exact same optical signature on both. So what could it actually be? Scientists don't have a confirmed answer yet, and it's important to say that clearly, because a lot of the noisier corners of the internet will happily fill that gap with speculation dressed up as certainty. What we do have are informed hypotheses, built from decades of understanding how these kinds of icy, organic-rich worlds behave chemically over time. The leading idea centers on complex organic chemistry. Both Titan and Pluto are known laboratories, in a sense, for a class of reactions that scientists have been studying for years. The slow, cold construction of complicated carbon-based molecules out of simpler building blocks like methane and nitrogen, driven by sunlight, cosmic rays, and other forms of radiation striking their surfaces and atmospheres over millions or billions of years. On Titan, this process is thought to be responsible for tholins, the sludgy organic haze that gives the moon its hazy orange look. On Pluto, similar processes are believed to paint parts of its surface with that reddish-brown tint captured so vividly by New Horizons back in 2015. If both worlds are independently cooking up similar organic compounds through similar radiation-driven chemistry, even starting from different raw ingredients and running at different temperatures, it's not entirely implausible that some specific, currently unidentified molecule could be a common product, something that keeps showing up because the underlying physics that builds it is universal, not local. But that's a hypothesis, not a confirmed identification, and scientists studying this signal have been very careful to say so. Because here's the deeper problem. This wavelength doesn't cleanly match any molecule currently sitting in the spectral libraries astronomers use to identify compounds from a distance. Those libraries are enormous, built from decades of laboratory spectroscopy on everything from simple gases to complicated organic tars. And this signal simply isn't a clean match for anything in them. That leaves a few real possibilities on the table. It could be a genuinely novel molecule, something that has never been characterized in an Earth laboratory because it simply doesn't form under the conditions we normally work in here. It could be a mixture, an overlapping blend of several known compounds whose combined signature creates something that looks unfamiliar, even though its individual ingredients are not. Or it could be a known molecule sitting in an unusual physical state, a different crystal structure, a different temperature regime that shifts its normal signature just enough to make it unrecognizable against the standard reference data. Each of those explanations is scientifically reasonable. None of them has been confirmed, and that gap between a confirmed real detection and a confirmed identity is exactly the space where a story like this either turns into responsible, careful science journalism or spirals into wild, irresponsible clickbait about aliens and impossible physics. Let's be clear about which one this actually is. Nobody serious in this field is suggesting extraterrestrial life, artificial signals, or anything that breaks the laws of chemistry. What they are suggesting, and what makes this genuinely exciting even without any of that exaggeration, is that there appears to be an entirely new class of chemistry happening on multiple worlds in our solar system that we simply did not know about before Webb was powerful enough to detect it. That by itself is remarkable. We are talking about the most sophisticated infrared telescope ever constructed, a machine that took decades to design, billions of dollars to build, and a rocket launch so precise it had almost no margin for error, unfolding itself in space 1 million miles from Earth, cold enough and quiet enough to detect the faintest whispers of infrared light from the edges of the solar system and beyond. And even with all of that extraordinary engineering behind it, This telescope is showing us that there are still basic chemical mysteries sitting on our own cosmic doorstep, on worlds we have already visited with spacecraft, already photographed in stunning detail, already thought we understood reasonably well. This is also a good moment to talk about how strange Pluto has turned out to be, generally once instruments capable enough to study it in detail were finally trained on it. For most of the 20th century, Pluto was basically a dot, a tiny distant point of light discovered in 1930, so far away and so small that even our best telescopes could barely resolve any detail on its surface. It sat in scientific limbo for decades, its exact size uncertain, its composition guessed at rather than measured. Then in 2015, NASA's New Horizons spacecraft did something no human-made object had ever done. It flew directly past Pluto after a 9-year journey across the solar system. And in doing so, it shattered almost every assumption scientists had quietly been making about the place. Instead of a dead, uniformly cratered ball of ancient ice, New Horizons revealed a world of astonishing complexity. Enormous nitrogen ice plains, smoother than almost anything else in the solar system. Mountain ranges made of water ice, rising kilometers into a thin, hazy sky. Evidence of possible ongoing geological activity on a world that, according to older models, should have been frozen solid and inert for billions of years. And then, years later, when Webb turned its infrared eyes toward Pluto, it added yet another layer to that picture. Scientists studying Webb's mid-infrared data found that Pluto's high-altitude haze, the same kind of thin atmospheric layer that gives the dwarf planet its subtle blue color when photographed from certain angles, plays a much bigger role in driving its climate than anyone had predicted. This wasn't a brand new idea out of nowhere. Back in 2017, a team led by planetary scientist Xi Jiang had actually predicted, based on theoretical modeling, that Pluto's haze should make the world unusually bright, at exactly the mid-infrared wavelengths Webb specializes in. At the time, there was no instrument sensitive enough to actually test that prediction. It just sat there, an educated guess waiting for technology to catch up. Then in 2022, once Webb's instruments came fully online and were powerful enough to separate Pluto's faint signal from the light of its large moon Charon, which orbits so closely that their thermal signatures used to blur together in older data, scientists finally got the chance to check. And the prediction held up almost exactly. Pluto's haze really was doing what the models said it should be doing years earlier. As Zhang himself put it at the time, it's genuinely rare in planetary science to see a hypothesis confirmed that cleanly and that quickly, once the right instrument becomes available. That confirmed haze discovery matters here for a specific reason. It tells us that Pluto's atmosphere and surface chemistry are far more interconnected, far more dynamic, and far more capable of producing complex outcomes than the old simplistic picture of Pluto as a frozen, inert rock ever suggested. A world with active haze chemistry, capable of driving detectable climate effects even with an atmosphere thinner than almost anything else we study, is exactly the kind of place where you might expect surprising, unidentified chemical signatures to show up. Pluto isn't a dead world, sitting quietly at the edge of the solar system. It's a chemically active place, still capable of producing genuine scientific surprises, more than 3 billion miles from the nearest observer. So when you put these pieces together, the picture that emerges is not one of Pluto suddenly breaking the laws of physics, or Webb detecting something that shouldn't exist according to any rule we understand. It's something more grounded and honestly more interesting than that kind of exaggerated framing. It's the picture of two very different worlds, one wrapped in thick orange haze near Saturn, one frozen and distant at the edge of known space, both independently producing the same unidentified chemical fingerprint through processes we don't yet fully understand, using instruments only powerful enough to catch this kind of subtle detail for the first time in human history. That's not impossible. That's the frontier of planetary science actually working the way it's supposed to, instruments improving, old assumptions getting tested, and every so often, the universe handing scientists a genuine puzzle instead of a confirmation of what they already expected to find. There's also a bigger reason planetary scientists care about this beyond simple curiosity about one strange spectral line. Titan and Pluto are both considered, in different ways, useful chemical analogs for understanding processes that may have shaped the early history of our own planet. Titan in particular has long fascinated scientists interested in prebiotic chemistry, the kind of basic organic reactions that billions of years ago may have eventually led toward the building blocks of life here on Earth. Its atmosphere, rich in nitrogen and methane, constantly bombarded by sunlight and cosmic radiation, is often described as a kind of natural laboratory, running chemical experiments over geological timescales that we can only simulate in small, imperfect ways here on the ground. If Pluto, despite being a completely different kind of world, is independently generating some of that same complex chemistry, it strengthens the idea that these organic building processes aren't some rare fluke unique to one specific set of planetary conditions. They might be a more general, more universal feature of cold, icy, radiation-exposed environments across the solar system, and potentially, by extension, across other solar systems as well. That's part of why researchers studying Pluto's haze have specifically pointed out that understanding its chemistry could offer clues about the conditions that made early Earth habitable in the first place. Our own planet, billions of years ago, was a very different place than it is now. A hostile, chemically active environment bombarded by radiation, slowly building up the organic complexity that would eventually make life possible. We can't travel back in time to study that process directly. What we can do is study places like Titan and Pluto, worlds that in some ways still resemble earlier, more primitive chemical environments, frozen in time at the edge of the solar system, largely untouched by the kind of planetary scale transformation Earth went through. Every new discovery about how organic molecules form and behave on these distant worlds adds another small piece to an enormous, ongoing puzzle. How do simple chemical ingredients, over enough time and under the right conditions, eventually organize themselves into something as complex as life? None of this means scientists are claiming Pluto or Titan harbor life or anything close to it. That's an important distinction to hold on to, because it's exactly the kind of nuance that gets stripped away the moment a story like this hits certain corners of the internet. What we're actually talking about is basic organic chemistry, the kind of molecule building processes that are considered necessary precursors to life, not evidence of life itself. Finding an unidentified molecule that shows up independently on two very different icy worlds is scientifically exciting because it suggests these organic chemistry processes might be more widespread and more robust than previously thought, not because it suggests anything is currently alive out there. So where does this leave us right now in terms of what actually happens next? The research team behind the Titan and Pluto detection has been working to formally publish their findings, with the study expected in the journal Astronomy and Astrophysics, a respected peer-reviewed publication that specializes in exactly this kind of planetary and astrophysical research. Peer review matters here more than it might seem like it should. It means other independent experts in the field, people with no stake in this particular team's reputation or funding, get to examine the data, check the methodology, and try to poke holes in the conclusions before they're accepted as a solid scientific contribution. That process takes time. It's slower and far less dramatic than a headline promising something impossible, but it's also the entire reason we can trust scientific findings that survive it. In practical terms, scientists studying this mystery signal are likely to pursue a few different lines of investigation going forward. They'll keep gathering more Webb observations of both Titan and Pluto, looking for the signal under different conditions, at different times, potentially at different locations across each world's surface, to see whether its strength or exact characteristics change in ways that might hint at its source. They'll almost certainly try to recreate the signal in laboratory conditions here on Earth, using specialized chambers that can simulate the extreme cold, low pressure, and radiation environments found on Titan and Pluto, testing different combinations of simple molecules to see if any produce a matching absorption feature at 5.113 micrometers. And they'll likely look for the same signature on other icy worlds, across the solar system, other moons, other distant objects in the Kuiper belt where Pluto itself resides, to see whether this mystery chemistry is a two-world coincidence or genuinely widespread phenomenon we've simply never had the instruments sensitive enough to detect before now. It's worth pausing here to appreciate just how new this kind of capability actually is. The James Webb Space Telescope only became fully operational in the summer of 2022, after a famously nerve-wracking launch and deployment sequence in which literally hundreds of individual mechanisms had to work perfectly, with almost no possibility of repair if something went wrong, a million miles from Earth. Before Webb, our ability to study the faint infrared chemical fingerprints of distant cold worlds like Titan and Pluto was dramatically more limited. Earlier space telescopes and ground-based observatories simply didn't have the combination of sensitivity and infrared range needed to pick apart signals, this subtle from objects this far away and this cold. Pluto, remember, is so distant and receives so little sunlight that it's an extraordinarily faint target even for a telescope as powerful as Webb. Extracting a clean, reliable, precisely located absorption feature from a world that far away and confirming it independently across two separate instruments represents a genuine technical achievement on top of the scientific mystery itself. That's part of why discoveries like this feel like they're accelerating right now in this specific window of time. We're not just getting new data about old questions. We're getting an entirely new category of data that simply didn't exist before, because the instrument capable of collecting it didn't exist before. Every time Webb turns its attention toward a familiar object, a planet, moon, or distant world we thought we already understood reasonably well, there's now a real possibility that it will reveal some detail invisible to every previous generation of telescope. Pluto and Titan happen to be two of the more recent examples, but they almost certainly won't be the last. Distant icy moons of Uranus and Neptune, sitting largely unexplored since brief flybys decades ago, remain tempting targets for exactly this kind of detailed infrared spectroscopy. Countless smaller Kuiper belt objects, distant cousins of Pluto scattered across the outer solar system, have barely been studied at all in this level of chemical detail. If this exact mystery molecule, or something related to it, turns out to be more widespread than just these two worlds, it would suggest we're looking at a genuinely important, previously invisible piece of solar system chemistry, something that's apparently been sitting there the entire time, simply waiting for an instrument sensitive enough to not. So, to bring this back to where we started, is this impossible in the sense of breaking any known law of physics or chemistry? No, and it's important to be honest about that instead of chasing the more sensational framing. Nothing about this discovery suggests our understanding of chemistry or physics is somehow broken. What it suggests, more precisely and honestly, is that our catalog of known molecules remains incomplete, that the chemistry happening on cold, distant, radiation-exposed worlds is more complex and more surprising than our existing reference libraries currently capture, and that even after New Horizons, even after decades of study, even after everything we thought we understood about places like Pluto and Titan, there are still genuine mysteries waiting out there at the edges of our solar system. Is it stunning? Genuinely, yes, and not because of exaggeration. It's stunning because two worlds that shouldn't share almost anything in common, chemically or environmentally, are apparently producing the exact same unexplained signal, confirmed across multiple instruments, checked and rechecked by independent researchers currently sitting on the desks of some of the most experienced planetary chemists in the world, and none of them can yet tell you exactly what it is. That's not a manufactured mystery designed to generate clicks. That's the actual, current, honest state of a real scientific investigation happening right now, in real time, using one of the most sophisticated pieces of technology humanity has ever built. We'll be watching closely as the formal study makes its way through peer review, and as more Webb observations come in from both Titan and Pluto over the coming months. If you want to understand the universe a little better than you did 5 minutes ago, that curiosity, that willingness to sit with a genuine unanswered question instead of demanding an immediate, tidy explanation, is exactly the mindset that got us this far in the first place. Somewhere out there, on two worlds separated by roughly 1 billion miles of freezing, empty space, a molecule nobody has ever identified is quietly absorbing light at 5.1113 micrometers, waiting for someone, somewhere, to finally figure out exactly what it is. Let's slow down for a moment and really sit with the scale of what's being described here, because it's easy to let a number like 5.1113 micrometers slide past without appreciating how precise that actually is. A micrometer is 1/1,000,000th of a meter. The difference between one wavelength of light and a slightly different one, off by even a tiny fraction of a micrometer, is the difference between two completely different molecules. Spectroscopy, the science of reading these light fingerprints, works because these gaps are astonishingly precise and astonishingly consistent. A molecule doesn't absorb light in some vague, roughly defined range. It absorbs at an exact wavelength, dictated entirely by its own internal structure, the specific way its atoms are bonded together, the way they vibrate and rotate in response to incoming light. That precision is exactly why this detection is being taken so seriously. If the Titan signal and the Pluto signal were only roughly similar, close, but not identical, scientists would have far less confidence that they were looking at the same underlying molecule. But this signal lines up closely enough, at the same precise point in the spectrum, on two separate instruments, on two separate worlds, that dismissing it as coincidence becomes very difficult to justify. It also helps to understand just how much groundwork had to happen before a discovery like this was even possible. For decades, scientists studying the outer solar system worked with data that, by today's standards, was almost unbearably limited. Ground-based telescopes, even excellent ones, have to fight through Earth's own atmosphere, which absorbs and distorts huge portions of the infrared spectrum before that light ever reaches a detector. Earlier space telescopes, remarkable as they were for their time, simply weren't built with the specific combination of infrared sensitivity, spectral resolution, and cold operating temperature needed to pick apart signals this faint from objects this far away. Webb changes that equation entirely. It operates at a temperature only a few dozen degrees above absolute zero, cooled by a multi-layered sun shield roughly the size of a tennis court, specifically so that the telescope's own heat doesn't drown out the faint infrared glow of the distant objects it's trying to study. That kind of engineering isn't just impressive for its own sake. It's the literal reason a signal this subtle from a world as distant and dim as Pluto could be detected and confirmed at all. There's also a human side to this story worth pointing out, because science like this doesn't happen in a vacuum, produced by machines alone. It happens because specific researchers, working through mountains of raw data, noticed something that didn't fit, and had the scientific instinct to ask a simple, curious question instead of dismissing it. That moment, one scientist reaching out to a colleague working on a completely different world, asking whether they'd seen the same strange gap in their own data, is really the heart of how discoveries like this unfold in real life. It's rarely a single dramatic breakthrough. It's usually a quiet, careful process of comparing notes, double-checking assumptions, and slowly building enough independent confirmation that a strange anomaly becomes an accepted, credible finding. That collaborative instinct, checking your own surprising result against someone else's completely separate dataset, is exactly the kind of rigor that turns an interesting glitch into a genuine scientific discovery. It's also worth remembering how young this specific chapter of solar system exploration still is. Pluto spent nearly the entire 20th century as barely more than a smudge of light in even the best available telescopes. It wasn't until New Horizons swept past it in 2015, after a journey of more than 9 years across the solar system, that humanity got its first real detailed look at the place. Before that flyby, entire textbooks confidently described Pluto in ways that turned out to be wrong within days of the spacecraft's closest approach. Complex geology where scientists expected a dead, static surface. Evidence of relatively recent activity on a world assumed to be ancient and frozen solid throughout. Every leap in observational capability, from New Horizons cameras to Webb's infrared spectrographs, has revealed Pluto to be stranger, more active, and more chemically interesting than the version of it that existed in scientific consensus just a decade earlier. This new mystery molecule fits into that same pattern perfectly. It's not an isolated oddity. It's the latest entry in a growing list of ways Pluto keeps refusing to behave like the simple, frozen, inactive world it was once assumed to be. The same is true, in a different way, for Titan. Long before Webb, Titan had already earned a reputation as one of the strangest and most chemically rich places in the entire solar system. NASA's Cassini mission, which spent well over a decade orbiting Saturn and repeatedly flying past Titan, revealed a moon with actual liquid seas and lakes on its surface, not water, but liquid methane and ethane, cycling through an alien version of Earth's own water cycle, complete with clouds, rain, and river channels carved into its icy crust. The European Huygens probe, which Cassini released to parachute down through Titan's thick atmosphere in 2005, sent back the only images ever taken from the surface of a world in the outer solar system, showing a landscape of rounded water ice cobblestones sitting in a hazy orange haze. All of that groundwork, all of those earlier missions, built up the detailed picture of Titan's chemistry that made this new discovery possible. Scientists didn't stumble onto this mystery signal blindly. They found it precisely because decades of prior study gave them an extremely detailed map of what Titan's chemistry should look like, detailed enough that a single unexplained gap in that map immediately stood out as something worth investigating seriously. Put those two histories together, decades of Cassini and Huygens data building an intimate chemical portrait of Titan, and New Horizons' single precious flyby transforming Pluto from a distant dot into a fully realized world. And you start to understand why this particular discovery lands as hard as it does within the planetary science community. These aren't mysterious, unexplored places anymore. They're two of the most intensively studied objects in the outer solar system, examined by multiple spacecraft, multiple instruments, multiple generations of researchers. And even with all of that accumulated knowledge, Webb still managed to find something neither world's existing chemical map could explain. That's a genuinely rare thing to happen in a scientific field as mature as outer solar system studies has become. It's the equivalent of resurveying a well-mapped coastline with slightly better instruments and discovering an entire hidden inlet nobody had ever charted. None of this is likely to resolve quickly, and that's worth setting expectations around honestly, rather than promising some dramatic reveal just around the corner. Identifying a completely unknown molecule from a distance, using only its spectral fingerprint, is one of the more difficult problems in planetary chemistry. It typically requires painstaking laboratory work here on Earth, recreating the extreme cold and low pressure conditions found on Titan and Pluto, testing combination after combination of candidate molecules and comparing the resulting spectra against the signal Webb detected, looking for an exact match. That kind of work can take years. It's entirely possible we'll be watching this story develop gradually through a slow trickle of follow-up papers and conference presentations, rather than one single dramatic announcement. But that slower pace doesn't make the underlying discovery any less significant. It just means real science, unlike the version of it that gets condensed into a sensational headline, tends to unfold carefully, one confirmed detail at a time. What we can say with confidence, right now, today, is this. The James Webb Space Telescope has detected a real, independently confirmed, currently unidentified chemical signature on two dramatically different worlds at opposite ends of the outer solar system. That signature does not match any molecule in our existing reference libraries. It survived multiple rounds of verification across separate instruments and separate research teams. It's heading toward formal publication in a respected peer-reviewed journal. And it's forcing scientists who have spent entire careers studying Titan and Pluto to admit, honestly and openly, that there's still a piece of fundamental chemistry happening on these worlds that nobody currently understands. That's the real story behind the headline. Not aliens, not a violation of physics. Something arguably more compelling than either of those exaggerations. Proof that even in a solar system we've been studying for over a century, even on worlds we've already sent spacecraft to visit directly, there are still genuine mysteries hiding in plain sight, waiting for an instrument sensitive enough and a scientist curious enough to finally notice them.